I'm very happy with PyData again. Trying to push my message of R and Python can play nice together. So about me, my name is Linda. I'm a physicist by training. I like my space stringy rather than loopy. I moved into data science. I went from on-demand services, mainly caps, to now fashion, and I work as a data scientist at Lyst. Elsewhere, I'm very much into ballet, books, drawing, and photography. I have a ballet website, theballetback.com, so shameless plug. And I've been using Python since the late 2012. So that's me in a nutshell. So let me give you some motivation, and I'm going to start with this XKCD comic, because I love XKCD, and who doesn't like XKCD? So the first frame, we have a survival curve and a hazard rate curve. And unfortunately, this is a quite sad comic, because it's talking probably about some cancer diagnosis. And it's basically listing the survival probability. So it says basically there's an 81% survival probability for an individual to live up to 5 years, and 77% up to 10 years. So they talk about probability being a favorite branch of math, because it has many real-life applications. So the main point of this talk is to convince you that actually this set of techniques is very, very important. So let me give a very brief intro. Survival analysis is given to the name of statistical techniques that have to do with analyzing the timing of events, which namely this is duration data and its relationship with covariates. Now, traditionally, this has been the realm of medical researchers and actuaries, so lots of insurers, they have to be able to estimate, how long people are going to live, how long before they have an accident, etc., how long before they get sick. So typical questions are, what is the expected lifetime of patients given treatment A? What is life expectancy in London? But it's also widely used in engineering to look at failure in mechanical systems, namely reliability theory. But survival techniques have many applications in the industry. So typical questions might be, what is the time between sign up and first order use? When will a customer churn? How long before a tweet has no effect? When will a store run out of product? How long before a person replaces his or her phone? How long is the career of a football player? What is the expected lifetime of a Stark in Game of Thrones? So these are very, very deep and important questions. At Lyst, I've been involved in using survival analysis mainly in a project involving prediction of out-of-stock products. And you're going to be hearing a lot about Lyst elsewhere, because there are several Lyst speakers in this conference. So instead of me going and talking about fashion, I'm going to be talking about basically, first, I'm going to argue that survival analysis is a very useful set of techniques that can be used as part of a standard data science pipeline. This is acquiring, cleaning, storing, and modeling. Second, I'm going to expand on techniques to evaluate survival functions via random forest and generalized additive models. I'm going to keep advocating the use of Python and R according to the use case in hand. And finally, I'm going to show it explicitly by applying to a real data set. Drum roll, please. Academic careers. So the main question I'm interested in today is, what is the average lifetime of an academic career? And you might ask, why I'm interested in this particular question? Well, I was an academic myself. So, and lots of people came from academia into data science. So another comic from PhD Comics. So if you guys have done a PhD, you'll probably be familiar with this comic strip. So postdoc versus postdoc. So but before we start and going into academia, let me just give a very, very quick skim through what I call Survival Analysis 101. So some definitions first. The birth event is the time associated with the beginning of an observation period. The death event is the time associated with the end of an observation period, either by an event, end of the study, or withdrawal from it. And then censorship. We don't always see the death event occur. So if you're thinking of medical studies, the study might end before people, die, or other type of thing happens. So the current time or other events will censor us from seeing the death event. So this is an example. So the blue, basically there's days from the start to 6,000, so it's long period of time. So the red observations, the points signify the death events, and then the blue ones is basically individuals who haven't died. And basically, this is a particular sample from my academic data set that I'm going to explain and enlarge in this talk. So a survival function looks like this. This describes the probability that the system will survive beyond the time t. Is basically this probability. And the survival time t, or the death time, may be thought as a random variable. So basically at the beginning of time, well, chances that you've survived is 1. And then as time passes by, that probability decreases monotonically. Another very interesting or important function is the hazard function. So the instantaneous hazard rate describes the probability that the event t occurs in t plus delta t, given that the individual is alive at t. And I know that this is a bunch of formulae, but the most important thing is the bottom line relationship between what is going to be the cumulative hazard function, which is just the integral of that lambda, and the survival function, which I presented before. I'll leave this at the slides for your reference. And well, the question is, if you have any of these curves, you'll be able to say a lot about the population itself. You'll be able to say, hey, the median lifetime of this population is X years or X days. And you'll be able to say, well, by this point, this is the number of failures that I've observed, or I haven't. Sorry, microphone. So there's some ways of giving an estimate of this survival curve or this hazard, a cumulative hazard function. So the first one is the Kaplan-Meier estimator. It's a non-parametric, oh gosh, that's a mindful, maximum likelihood estimate of the survival function. It is a step function with jumps at observed event times. So if SI represents all the individuals that have died at time TI, and RI is a risk associated from these individuals in this period of time, then you can basically compute this, and it will look like a little rag-like curve, which will be a very good estimate to the survival curve. And likewise, the Nelson-Allen estimator is an equivalent formula for the cumulative hazard function. So, okay, so that was like a very, very quick, roundabout through survival 101. So now I'm going to be going into an actual use case, namely surviving in academia. So let's first explain what is life in academia for all people that haven't been an academic. So people go and do a PhD, and then they might do a postdoc, then they might do another postdoc, they might do another postdoc, they might do another postdoc, and then some of them might get tenure. And those have survived for a long time. Others will probably die on the pathway. So the interesting thing about this problem is, first, how do I get a population for which I can apply these techniques and basically answer this question? Because how can we define, there's not like a unified database where I can go and basically say, oh, individual A, this is a name, they did their PhD, started this year and then this year. It's all over the place. And then depending on the area, PhDs might be longer or shorter, part-time. So there's many variables there. But at the end of the day, if you're an academic, you're probably going to be publishing research papers. So these are going to be the event signaling if a person is still in academia. And now we have online repositories and portals. So many papers can be found as electronic preprints, and in particular in many fields of mathematics and physics, all scientific papers are self-archived. So if I go and decide to pick an area where basically they all publish papers as preprints online, I'll be able to piece back all the lifetimes of individuals that are continuously publishing because they're academics. There's also open access digital libraries that combine literature databases with author metadata. So I could potentially also get additional covariates in terms of affiliations, where they're publishing their papers, if they do this with other people, where are these people, in which institutions they are, etc. So it's a very, very rich database. So in my particular case, because I did physics, and I know that in the high energy physics field, we basically always put papers on the archive preprint system, then I have a very, very high confidence that I'll be able to know if a person is still in academia or not. Now, authors that have published a preprint in the HEPTH, which is the High Energy Physics Theory archive, you're all very welcome to go and explore because there's an API available. And basically what I'm going to do is to subset to all authors whose first paper was between January 2000 and January 2015, and that had more than 2 papers. So this is the rough idea. I'll be explaining with more detail as I go. And this is just a very, very snapshot of a very, very horrible function that basically just signifies get data from the hepth physics repo, start n, date n, and then just dump it on a CSV and then just give it back. So at the end of the day, I got like a ginormous data frame where I can see all the titles of the papers, the abstracts, the authors, first name, surname, the categories, when it was created, because of course it can be republished, and the ID and the DOI if it later made it to a journal. So that's okay. And this is just something interesting. So these are a number of preprints per year. Now the archive started, I think, in 1992. So although there's a couple of papers that appear before, but very, very few. So you can actually see these little bars. But you see this is like increasing. So lots and lots of preprints. Of course, there's cross-listings, but I'm not going to get into that game at this stage. And then this is also a line plot of the author's first paper. So basically counting how many first papers appear in each year. Of course, because 2006 hasn't finished, you have that drop at the end. But you can see there the behavior. Now, I also need some covariates to basically be able to model, what basically makes people leave academia. And what are the factors that influence a long lifetime in academia? Is it that you managed to do your PhD in a good institution? Is it that you published a lot? Is it your gender, etc.? So the first thing is, well, I'm going to try to get some additional metadata. And for that, there's the Spires portal, which also has an API. And you can also get all the information for a given name. You can get their affiliations. You get the number of papers, their co-authors. So you can get a very, very rich set of data. The small print, of course, is a beware of authors' names, because how people go and write their names on the paper, unfortunately, is not consistent. So if you have two names, if you sometimes put accents or not, depending where you are, you might be identified as different people, even though you're the same individual. And to be fair, Spires works a lot to try to be able to coalesce all these results. But there's some, errors as expected. So there again, there's a very snapshot of the type of options you can pass to the API. You can get all the information in JSON back. You can basically extract more information than what I actually got. But in this way, by first getting all the author's name from the archive, then I just make a huge pickle of authors, and then I just go and call this API and get all the metadata for those authors. So this is the raw output. So I got data for over 25,000 authors. There's, of course, many issues with data involving consistency of names, affiliations, missing values, etc. But then for a given author, I can basically list all possible affiliations, which was their first institution, the paper, the number of authors, when was the first paper published, and the full listings. So this is just a very, very small example. And then, of course, you have to go to the whole issue about data cleaning. And a pain particularly was the affiliation cleaning, because, again, it's a matter of names. So, for instance, you can have this list of affiliations, and here you can observe, King's College London, and then King's College London, Maine, and then King's College London, Department of Maths. And this is for the same individual. And if I don't do anything, I would count this as 3 affiliations, when actually it's just 1. So you need to find a way of really cleaning this to something that is much more consistent and that just coalesce these 3 results. The other thing, of course, is that sometimes people might be visiting another institution, and then they might put multiple affiliations on the same paper, so that makes the problem even more complicated. But anyway, that's a subject for another talk on cleaning data and parsing strings. But this is the type of thing that we need to do in order to acquire data for survival modeling. So we need to extract timestamps for first and last paper, calculate iterations, and determine if the observation is censored. How I define the time on which I was gonna decide to end my study was based on observing the average publication time across my population. So I realized that actually there's times in which people go over a year and a half without publishing. So then I had to allow for some time to be able to decide, oh, this guy has definitely churned from academia or hasn't. So I decided January 2015 to give me some wiggle room for the 2015 period in case, they basically would publish something that year or they haven't published something just beforehand. And then, of course, I also parsed all the timestamps so I could extract the date of first paper, date of last paper, survival time in days, and average publication time. Now, of course, there's some errors in this approach because maybe when you publish your first paper, you were in your master's, or maybe if you publish your first paper, you were already 1 year, 2 years into your PhD. So, of course, there's going to be this sort of like plus minus 1 year error. The master's, I actually sorted it out by counting the number of papers. But anyway, that's details. But at the end of this very long story, you end up with a ginormous data frame, 1 row per author, which has all the information that you want. And it's awesome feeling to feel like you have achieved this thing. Here's essentially some of the comments that I mentioned before, cross-listing. And there were, of course, some outliers because of the cross-listing issue. Say that you participated on these ginormous collaborations, like LIGO, then those papers have like gazillion authors. So then you just go and say, oh, first, like number of authors on first paper, 127. And you're like, So if I want a model with a covariance saying the impact of the number of papers on your PhD or number of co-authors in your PhD, and basically you have all these huge, ginormous numbers, that's a big outlier. So then you have to basically try to subset your data further in order to get a good description of the population as a whole. So we kept authors who have reasonable numbers, quote unquote. So average number of co-authors is less than 6, which was I looked at the percentiles and then just decided, okay, this makes sense. Less than 190 effective papers. Effective means that basically was not one of these ginormous collaborations. Able to determine their PhD affiliation, that people that had more than 1 paper, that the average publication time was less than 5 years. The number of papers is less than 185. And the number of co-authors in their first paper is less than 20, and the number of papers in their PhD is less than 32. So we were left with a sample of 4,244 authors. And then we created some derived features because I wanted to analyze this covariate, so buckets for co-authors, co-authors in first paper, average publication time. All this feature selection came almost from experience and from me understanding how it works. I basically classify authors and assign genders using the GenderAce.io API. So basically have a huge database of names, and then they give you if it's female or male with some probability. There's a flag if you are independent researcher or a more collaborative one based on the ratio of number of solo papers versus papers with more authors. Censoring flag. Top university, which was generated by listing the top 20 universities in the sample and created a flag if the author's PhD was from one of these. And these are the ones that appeared just from my analysis, but then there's some caveats about the names because of what I told you. So we were left with this total. 3,220 could be assigned a gender, and 760 of these were flagged as having done their PhD in a top university. And these are some interesting data nuggets. So the gender ratio, 10% female, 66% male, 24% undetermined. Although actually the percentage for females much more less because some probabilities associated with those names are actually quite low. So for instance, it classified Aninda as female, and most of them were Indian, and I know for a fact they were male. So you get this type of quirks. Asian names also were very tricky to guess. So yes, that is an issue. The average number of papers during the PhD was 5.2, which I thought it was quite high. However, it has been decreasing in the last 5 years towards 4. The figure for female stands at 5 and for male 5.4. They have equivalent number of co-authors on their first paper. Also, with the demand probability of gender matching to be over 80%, the difference is wider, and sample size decreases from 433 to 349, and some other types of nuggets. So, okay, tools. So if you're going to do survival analysis, you can go to Python and just Google survival Python, and you'll probably find Cam Davidson-Python's Lifelines, which is a very good library. It's built on top of pandas, includes non-parametric estimators, regression, and various utility functions. And the API is very similar to scikit-learn, so you can basically start doing stuff out of the box. In R, there's like huge amount, so but huge. So I just put some of the most visible ones, but there's too many. But in that page, there's like summary of every single library that you can find. So let's application. So again, a PhD comic talking about the difference between interning and postdocs. So here are basically my estimates using the data that I pull out for the survival and the hazard curve. The median lifetime here was of approximately 9 years. And this is the typical Lifelines call. So you create a fitter object, you pass your durations, you pass your censoring flag, and then basically you fit it to that object, and then you can plot it. And there's lots of functions that allow you to obtain the median lifetime, which are just acting on the object. So it's quite straightforward. Basically, here we see how this probability decreases. Of course, for the longer lifetimes, we'll have only contributions coming from individuals that did their PhDs on the early 2000s. So there's less and less data for this side of the curve, whereas there's more data on this side of the curve. So these are complementary boxes. And this is basically now starting to split by different covariates. So here you have male and female, and also you have the hazard curve, and then you have the lifetime. So 9.7 years for men and 7.2 years for women. But the sample for women, I'd say that is very, very small. So there's errors there. This is like for the top 20 universities, and it's quite fun to see what's going on. Basically, this is for my own amusement, and you should later go and look at the slides. But Oxford is quite stable. And in other, like in the Japanese universities, Tokyo and Kyoto, you sort of like have like very abrupt falls, and then it's very stable. So there might be some sort of cultural explanations to try to see why that's the case. I don't know if students there tend to stay there as postdocs or they go abroad, etc. And then, of course, you have factoring by the different covariates. So I bucketed the average publication time and the number of co-authors. So the general message is publish a lot and have lots of co-authors. You have lots of co-authors, you publish a lot. So there's some interdependence here. And those are the buckets. And if I had more time, I would explain more. But I have still a bit to go. And this is basically how important is the number of papers on your PhD. So your hazard rate will be higher if you do just 1 or 2 papers on your PhD. But if you did from 7 to 31, it's much less. So again, publish a lot. And then that's the difference between doing a PhD in a top university or not. It's very, very close. You can do the same thing in R. So these are the typical libraries, the survival library. The call is very simple. This basically creates the served object, and then you just fit it, and then you plot it. This is a wrapper on ggplot that gives you that very, very nice graph. And these are the type of objects that you can find on the fitted object. Now, we've done these non-parametric estimates, but then we would like to be able to construct this curves for individuals, and we would also like to do prediction tasks. So the tool of all trades is the Cox model, which is a proportional hazard model. So the most interesting analysis examines the relationship between survival and one or more covariates. So the simplest thing you could try to do is to write the hazard in this form, so exponential of some linear combination of functions. And this was then superseded by Cox model, which leaves the baseline function, so that alpha, separate and unspecified. So that's why it's called semi-parametric, because that is completely free and it will be just fitted according to the data that you have. And so then basically you just have your baseline hazard, and variations of 1 unit on each covariate will have a multiplicative effect on the baseline hazard. So that's what that expression is telling you. And to estimate this model, Cox introduced a method called partial likelihood that I'm not going to bore you with. But that's what Lifelines uses to estimate and fit the model. There's also other types of models, like the additive hazard models. So when the covariates are time dependent and you can't use the Cox model, you could use this one. So basically you have a scalar product, so that's why it's additive model. And the matrix Y uses all the risk information, and the vector alpha contains all the covariant regressors. So then you can basically build an estimate for the hazard rate. So this is again applying the Cox model to a very, very dumb combination of models. So here I just use the number of PhD papers and the number of authors in your first paper as covariates. I use the PATSI library in Python that allows you to write R-like formulas. It's like one-hot encoding, like done very quickly, but you can also build interaction terms out of the box. So then this is the summary, and here you can basically start making statements such as, if you do here the baselines are individuals who had 2 or 4 papers during their PhD with 1 or 2 authors in their first paper. So this tells me that if you had an individual has a number of papers under their PhD on the 1 and 2 bucket, you have 1.45 times the hazard rate over the baseline. So you can make statements as to the difference in risk depending on the different values of the covariate with respect to the baseline. So if you add the year as a factor, with 2000 being the baseline, we find that individual starting on 2010 has 2 times the hazard rate. So he'll be less likely to survive. If you add gender, with female being the baseline, we find that a male has 0.91 times the hazard rate. And but building a model much more complicated with gender, co-authors bucket, publication average bucket, and university, you find other interesting tidbits. So like the baseline of Cambridge University, and if you're female, number of authors in first paper 0.2, or co-authors bucket is from 2 to 3.4. You can basically make statements about the relative hazard between different institutions or between different numbers of papers or different co-authors. So I have 5 minutes left according to my iPhone. So model performance. So you can use the concordance index to evaluate the model, which is a generalization of the area under the ROC curve. And as a callback to my first PyData London, I'm going to explain it using my favorite show on TV. So consider all possible pairs of patients, at least one of whom has died. So hi, Jeffrey. So then you take a pair of patients, and then if you predict the survival time for John, and this happens to be larger than the predicted survival time for Geoffrey, you call this concordant with the outcome. And if you pick another pair of patients, but the predicted survival time for Danny is less than the predicted survival time for Geoffrey, then you call it anti-concordant with outcome. So you can basically compute this index, and 0.5 would be your concordance index if you have random observations. And basically, if you do cross-validation of the model that I presented before, you get that your models have a concordance index of around 0.68, 0.69. So this means that it's performing well. And then this is the equivalent for R. And this is something called it's Schoenel residuals, and it's to test if the hypothesis of your covariance not varying with time is true, and of course it's not true. So that's why you use the Allen model. And very, very quickly, what happens if you want to apply these techniques to very, very big data sets? If you actually go and see the implementation of how you compute the Cox model, or both in R and Python, you see that it's actually quite intensive. So if you want to run it for a very, very big data set and for covariates that have lots of levels, namely categorical variables, it will take forever, and probably you won't be able to do it. So then you hit a wall. So then you have to find other approaches to give an estimation of the survival curve. So you can use generalized additive models, which is, I was going to explain, but of course I'm going to be running out of time. And you can just think logistic regression, and that will give you already the gist of what you're doing. You have a link function, and then you have a linear combination of smooth functions that are really like splines, and then you can fit a baseline hazard on it. So I'm going to skip this. But essentially in R, there's a library called MGCB, and this implements GAMS in R, but it has a function called BAM that is special for big, big, big data sets, and you can parallelize in different clusters. So basically, you can build your GAM, and you can actually build an estimate for the survival curve. So these are the typical calls. The other thing you can do is you can use random survival forests. So the library random forest SRC basically has now coalesced. If you've used random forest in R for either classification or regression tasks, then you already know how to do it, but instead of having, your categorical data or your numerical data, now you have durations data, and it's the same type of calls. The bonus points for this type of approach is basically that you only have to fix 3 parameters: the number of randomly selected predictors, the number of trees to grow, and the splitting rule. And there's no assumptions about proportional hazards or time-dependent covariates or anything. So you can just go and play with it immediately and just train your forest. And so this is the typical call. It's exactly the same if you've done random forest before. And then I basically did the same model for the Cox model, so you could then compare it. But this is basically for the training state. It evaluates every single survival curve for all your individuals. And then those are the predictions for the test set. So I've just plotted them for you. So those are all people in academia that might, with their probabilities of remaining or not. And you can also get variable importance as a freebie. So here it says that the number of pages on your PhD is the most important variable in order to basically predict survival probability. Then the number of the average number of co-authors that you have in your papers. So if you have, again, lots of co-authors, that's a good thing. Then the PhD place, et cetera, et cetera. So in my last 40 seconds, I'm just going to give you a very quick TLDR. So surviving academia, 9 years is the median academic life, and this is roughly equivalent to a PhD and probably 1 or 2 postdocs, depending on the length of your postdocs. Lots of papers during your PhD are a good indicator of survival, so publish or die. Be a good networker, so many collaborations equals many papers and opportunities. Then choosing the right place for a PhD helps because probably it facilitates the creation of networks. And finally, the data is consistent with trends of women in STEM. So, but the sample size for women was very, very small. On survival analysis, this is an extremely useful technique. It's applicable to many problems in various fields. There's a very good Python library with estimators and regressors. Thanks, Cam Davidson Pylon. More stuff available in R, so GAMS, Random Survival Forest. And there's other approach, Bayesian, and there was a tutorial on the subject yesterday that I hope you didn't miss. And thanks.
Thank you. We have time for questions.
Hi.
Hi. Since in your analysis the death event is non-explicitly observable, have you considered using a model that can deal with it?
Well, there were some death events that were observable because basically if I didn't see any paper like forever, after a while, I assumed that that person was dead. So basically if I didn't observe the death event after the 2015 like cutoff that I introduced, then I would consider that probably that person was still alive. And then I consider it as being a censored observation. But that was a decision I made based on experience of being an academic and knowing, if people don't publish in 2 years, they're probably just out. So, and then in order to test that hypothesis, I look at my population and looked at, the distribution of publication times to see if that was actually a sensible decision to make. But yeah, what you're suggesting might be another view, but I didn't explore that. So I stick with my original decision. In retail? Yeah. So I guess, customer churn would be a popular one if you do email marketing. For instance, Lyst, we're looking at auto-stock prediction. We sell clothes. So that's an interesting one to basically predict when products will go out of stock. If you're developing any type of, because I said it has applications on failure, if you are building products that they're basically gonna like washing machines or stuff and you're selling that, you might want to know when people will be likely to buy another one. So you might want to market to them. So I don't know exactly which, within retail, exactly what we're talking about, but I say that there's many, many different applications. In terms of, for instance, retail or in e-commerce particularly, you can look at, trying to model, from registration to first use, or if you're running membership services, like how long will they remain a subscriber before they basically quit their subscription, because then you might want to predict when to send them an email to say, don't go, this is an amazing offer. So I think within retail and marketing, those are the most natural applications, but there might be others.
Have you tried to look for other features? Because it seems your features are a little bit autocorrelated with what we're actually trying to predict, right? Obviously, if you stay in academia, you continue to publish. If you don't,
yeah, you're totally correct.
It's a weird also
Yeah.
useful in the sense of you use some features where you can really predict something. Have you looked at other applied?
So that's why I took this, you're totally right. I took the stepwise approach because I knew a priori that some features were likely to be heavily correlated, like for instance the co-authors with the number of papers, which is why I didn't look at the number of papers and just like the number of papers during your PhD. Because at the very least, I was demanding that you had 2 papers. And there's a huge amount of people that in their PhD, they only do 2 papers. So that was like my minimal requirement. And that was, I said like, oh, this is my initial feature, and I don't want to know about the rest because then that will be feedback into model. There's other features that one could try to do, but I would say that because of the complexity of just getting the data together, that's a hard thing to do. But it's something that, for instance, citations or like other type of networks, and there's different things that one can think of. But you're totally right. So this was meant more almost like a, exploratory fun thing. Oh, thank you. No, you're totally right, yes.
Can you compare the random forest technique to the standard technique in terms of how it performs and how system intensive it is?
So in the context of this particular one, it's hard to say because this data set was rather small. So in terms of like speed performance or like there's really nothing that you could say. In terms of accuracy maybe, but I didn't really run many different types of, I didn't play like parameter optimization within the random forest to be able to say, I found the optimal parameters in the random forest that basically break all performance. But the point that I was making here is actually you just, in like random forests in general, they're like your Swiss Army knife. It's like, I don't know anything, let's try this and see because I know it's robust, it doesn't tend to overfit. And the fact is that because of what I explained, even though I used the Cox model, in principle I shouldn't have used the Cox model because this covariance vary in time. So then you would need to do another approach. And in random forest, you don't need to make this type of assumptions. So, but I've read a couple of papers where they say that in some scenarios, actually the vanilla Cox model works better than the random forest, whereas in other scenarios, particularly when you have time variable covariates, then it's a very good technique. But the survival random forests are very recent. So I don't even know if there's an implementation in Python. I don't think there is. So I would be hard positioned to give you a concrete answer for this question.
Thanks, it was a really great talk.
Oh, thank you.
I'm just curious what the motivation for using it for out-of-stock prediction is as opposed to forecasting plus inventory.
Because we don't hold an inventory at Lyst. So that's basically it. We know very little about the products that the retailers hold. So we don't have all that extra information. We literally have timestamps. So that's the main motivation.
One question and one. First of all, it was very beautiful. The presentation was great, and I was wondering if it is shared somewhere.
I'm going to share the slides, which have all the snippets, and I'll be putting the code to extract the data on GitHub later on. I need to clean it a little bit. And I'll send the link to the organizers when the time comes.
Okay, thanks. And another question. Have you considered using also pre-literature, unpublished papers as a feature in the model?
Oh, sorry, unpublished?
Unpublished manuscript as a feature in the model.
Well, in many cases, these are actually unpublished because preprints are not necessarily published in a journal. And I actually didn't want to get into one extra feature that I could have considered was instead of just looking at total number of papers, here papers is really preprints, but a preprint could be a conference proceeding, it could be a series of notes that someone wrote for a lecture, it could mean many things. So you could partition that, for instance, for the type of journal that you published, because that will be a measure of the impact factor that publication had, and those will be other features. But it was more like, you know how they say that there's this cliche in data science that 90% of the time you spend doing cleaning and data and preparing your data, and then 10% of the time. So this is perfect example of that. But yeah, you could do that.
Okay, well, just the last question.
Just a quick comment. I thought it was very interesting. I was just wondering if maybe you could also do an analysis based on kind of subject area, for example, strings versus loops. What is the average age?
Totally.
Really interesting.
Actually, I was doing some using NLTK to do some text analysis on the abstracts to look at, like the words and you get, in HepTH, you get, of course, lots of string theory, supergravity. So, of course, supergravity is very high and all those other words. I think maybe loop appeared like 30 or 40 after removing all the stop words. But you could build features from that as well, I guess. So that would be a fun thing to do.
That'd be really interesting.
Yeah, definitely. So that's why I said, like, if I put this stuff on GitHub, maybe people can go and play with this data set because I don't have enough time to do so.
Okay, so lunch is served. Talks are back in 1 hour. So let's just thank Linda again.